In this example, we are going to use the rational zeros theorem to find the zeros of this polynomial and also write the function in factored form. So first, a quick recap of what the rational zeros theorem says. First of all, remember, it's only going to give you the possible rational zeros, and it's important that you remember what a rational number is. A rational number is a number that can be written as a fraction. So the theorem is going to give you a list of the possible rational zeros. To use the theorem, we have to look at the factors of the constant term divided by the factors of the leading coefficient. So looking at the polynomial in this example, first off, you want to ask yourself if the polynomial factors. So always try factoring first. That is our number one most efficient method for finding the zeros of a polynomial. However, if the function doesn't factor, that's when the rational zeros theorem is really handy. This function does not factor by any of our traditional factoring methods, so the theorem is going to be useful. So let's start by identifying the constant term. That's the term that does not have a variable attached to it. In this case, our constant term is -2. So we're going to list all of the factors of -2, both positive and negative, the numbers that divide evenly into -2, in other words, which would be both ±1 and ±2. And then we divide that by the factors of the leading coefficient, in this case, which is 5. So all the numbers that divide evenly into 5, which would be ±1 and ±5. So let's actually generate the list of all the individual possible rational zeros by doing this division. So we'll start by taking the first number in the numerator, so that would be 1, and dividing it by the first number in the denominator. So 1 divided by 1 we know is just 1. And then of course we have both the positive and negative version of that. Then stay with the number 1 in the numerator, and now you're dividing that by the ±5 in the denominator. So 1 divided by 5 will be 1/5, 1 over 5. Then we're done with 1 in the numerator, so we'll move on to ±2, and we'll start off with 2, and we'll divide that by ±1. So 2 divided by 1 is 2, so we'll have both positive and -2. And then we'll have 2 in the numerator divided by 5 in the denominator. So 2 divided by 5 is 2/5. So ±2/5. So these are going to be, again, the possible rational zeros. So we're not guaranteed that all of these are going to work, but we know if there is a polynomial, but we know that if there is a rational zero, it'll be one of these values. So there's a little bit of guess and check that happens here. We just have to guess one of these values from this list and see if it's going to work. But of course, we want to be smart about how we go about this list. We want to work smarter, not harder. So we definitely would leave the fractions for last. We'll try those last. Always start with +1 and see if it works. And if it doesn't, then you'll move on to -1. So in this case, we'll go ahead and try +1. So you would try +1 with your synthetic division. Make sure you take a look at your polynomial and check to see if you are missing any terms. Remember, missing terms require that you put a 0 in for the missing term. We don't have any missing terms here, so go ahead and proceed with your synthetic division. So synthetic division is showing that our remainder here is -12. So that means when we plug +1 into this function, we're getting out a y value or an output of -12. And that means that 1 is not one of our zeros. So I always recommend that you just put a slash through your synthetic division and you go to try again. Or of course, you could just erase if you wanted to and try the next possibility on the list. So after you have tried +1, then please always try -1 next. Again, we want to be smart about how we go through this list of possible rational zeros. So again, I would recommend that you pause the video and you go ahead and test your own synthetic division skills. Let's see if -1 works. So I'm getting a remainder of 0. And again, remember what that means. That means if we were to input -1 into this polynomial, we would get out a y value of 0. And that means we have one of our zeros. So again, the value that we were trying up here, which was -1, this is going to be one of our rational zeros. So if you like to go ahead and begin listing down at the bottom your zeros, we just found one. Our first 0 is -1. Now I recommend that you go ahead and move to the right of your synthetic division to write down the resulting equation that you have here. The resulting equation is going to be 1 power less than what we started with. So we started with a 4th degree, so this is going to be a 3rd degree. So 5x cubed minus 22x squared plus 13x minus 2. We'll set that equal to 0, and we want to solve this equation, meaning we will look for 3 additional zeros. Remember, the original function that we started with here, this function was degree 4. Therefore, we're looking for 4 zeros altogether. We've already found 1, and now that means we need to find 3 more. Now, the reason I recommend that you write your equation off to the right-hand side instead of putting your equation down here is because there's a chance we're going to need to do another round of synthetic division. And if that's the case, it's much easier to stack your synthetic division one on top of the other rather than having to start over rewriting your values. So now we're looking at 5x cubed minus 22x squared plus 13x minus 2. As I said before, you always want to see if the function factors. So if this polynomial were to factor, we would want to factor it. Now it has 4 terms, and you might try to factor by grouping. That's a great idea. But look what happens if we group the first 2 terms and attempt factoring by grouping. Our greatest common factor would be an x squared. That would leave us with a 5x minus 22. And if we look at the back 2 terms, I could only factor out a positive 1, which would leave us with 13x minus 2. And because these quantities here don't match, we can see that this polynomial does not factor by grouping. So grouping is not going to work, and that's why I have to use this rational zeros theorem again. Now notice when you look at the constant, which is 2, and the leading coefficient is 5, we have the same exact possible rational zeros list. So we're going to still use the values from this list. Now we already tried 1 and it did not work. -1 did work, so then it would make sense next to move on to positive 2 and try that next. Then I would move on to -2 if positive 2 didn't work, and save the fractions for last. But I'm going to actually show you how you can utilize your calculator to make this process go a little bit faster. So you're still going to be showing me some work on paper, but technology can really help us speed up the process. So to use our calculator to help us go through our possible rational zeros list, we need to first enter our function in our y equals. So go to your y equals and let's enter the original function, which was 5x to the 4th. Remember, when you are in the exponent, you'll need to arrow to the right to get out of the exponent. Minus 17x cubed minus 9x squared plus 11x minus 2. Now, there are a few different ways to use the calculator to go through your possible rational zeros list. Some people will tell you to use the graph, and that works. However, I discourage you using the graph because you might waste too much time trying to find the appropriate window. That's also a bad idea because sometimes the zeros are fractions and you can't really tell the fractional values from the graph very easily. Another way of doing it is to use the table, but I discourage that for the same reason, because it can be time consuming to go through the table. So I'm going to show you what I think is the most efficient way of using your calculator to help you go through this list. And you want to go back to your home screen. So remember the quit button, it's above the mode. So second quit, go back to your home screen. And At this point in the problem, we already tried 1 and -1, so we were getting ready to try 2. So we want to put 2 into our function. So to do this, we want to find our y1, which is on this shortcut menu F4, which is in green. So you're going to have to hit the alpha button first. So I accidentally hit the second button. Let me go back. Alpha, and then the trace button, and that pulls up your shortcut menu. Here's your y1, and you're going to press enter. And then using the parentheses, you're going to input 2. So remember, this is the same as f of 2, or if the name of the function is p, this is like p of 2. Basically, the calculator is going to input x equals 2 into the function that's in our y1, and we will get our output. So our output, this is our y value. Our y value is -72, which tells us that 2 is not a 0. So then we'll go back to our possible rational zeros list and try the next possible 0, which would be -2. So alpha, F4, shortcut menu, choose the first one. Let's try -2. Make sure you use the negative button, not the subtraction button. You'll get an error if you accidentally use the subtraction button. When I put in -2, I get out 156. So -2 is clearly not a 0 either. Look back at your list. The only values left are the fractions. But don't worry, we're letting the calculator do this work for us. So let's try out our fractions. I'll start with the smallest positive one, which would be 1/5. So let's try 1/5. You can see you're not getting out a 0, so 1/5 is not a 0. Next, we would try -1/5. This is the process that you will get to continue to use to help you find at least your first 0 and sometimes even your second 0 before you go back to paper and you continue with your synthetic division. So -1/5 is not a 0 either. Back to our list, we've got +2/5 as our next option. So +2/5. And our output finally is 0. So that tells us that +2/5 is one of our rational zeros. So now we're going to go back to our paper and do the next round of synthetic division. So now that we saw that +2/5 worked on our calculator, we're going to go ahead and do our synthetic division with 2/5. But I'm going to stack my synthetic division here because notice I'm not going to use the original coefficients from the original polynomial. I'm using my new coefficients from the cubic, which will be the 5, -22, 13, and -2 to do my synthetic division. So we'll drop down the 5, and then we're multiplying 5 times 2/5. And I know the fractions initially might seem scary, but just remember it's 5/1. 5 divides into 5 once, so we really end up with 1 times 2. It really is more doable than it might initially seem. Then we add straight down, so that would be a -20. So now we're multiplying -20 times 2/5. That's -20/1. 5 divides into -20 4 times, or we could say -4 times. -4 times 2 is -8. Then we add straight down, +5, and we're back to multiplying 5 times 2/5 again. We just did that. We saw that was going to give us 2, and then we add, and we get a remainder of 0, which is exactly what we expected, remember, because the calculator verified that 2/5 was a 0. So again, we have another rational 0 here of +2/5. We can go down and add it to our list. So we have 2 zeros, we're looking for 2 more. Remember, degree 4, we want 4 altogether. So now let's write down the resulting equation. We're dropping 1 by our degree here, so this is going to be degree 2. So this is 5x squared minus 20x plus 5 is equal to 0. And now, because this is an equation which is degree 2, it's a quadratic equation. And once you get down to a quadratic equation, you certainly don't want to do synthetic division anymore. You want to go ahead and solve this quadratic by either factoring or using the quadratic formula. So First, I noticed that there is a greatest common factor of a 5, so I'll factor out 5, which will be 5 times the quantity x squared minus 4x plus 1. And now I'll work on solving x squared minus 4x plus 1. There are not going to be two numbers that multiply to 1 and add to negative 4, so unfortunately, this does not factor. So therefore, we will use the quadratic formula to solve x squared minus 4x plus 1 is equal to 0. Remember, you don't really need to do anything with that 5 out in front. If you wanted to think of it like this, you could essentially think of it as dividing both sides by 5. So really that 5 is not needed when we go to solve our equation. We're just solving x squared minus 4x plus 1 equals 0. So quadratic formula will give us the opposite of b. So in this case, that would be a positive 4 plus or minus the square root of b squared. Now make sure you have that negative 4 in parentheses, minus 4 times a times c, all divided by 2 times a. So this is another place where I would pause the video and make sure you can do your quadratic formula and simplify this. You really shouldn't need your calculator on this particular problem. The numbers work out pretty nicely. So we're getting 4 plus or minus the square root of 12 divided by 2. And then we do want to go ahead and simplify. Remember, when we're simplifying our square roots, we're looking for a perfect square that divides evenly into 12. So we're thinking of that square root of 12 really as the square root of 4 times 3, because 4 is a perfect square, and the square root of 4 will be a 2. So the square root of 12 will simplify to 2 times the square root of 3. And then we can divide that 2 not only into this 4, but also into this 2. So 2 divides into 4 twice, 2 divides into 2 once, and therefore our simplified answer will be 2 plus or minus the square root of 3. So those are my last two zeros, 2 plus or minus the square root of 3. And I'm going to write them as two separate values, 2 plus the square root of 3, and then 2 minus the square root of 3. And you can see that we have 4 zeros all together. Let me just classify these for you. Just as a reminder, these first two zeros of negative 1 and 2/5, those are your rational zeros. Those are rational numbers. Remember, you saw those two values here in your list of possible rational zeros. But the last two zeros that we got, those are considered irrational numbers. Remember that irrational numbers cannot be written as fractions. These are going to be decimals that go on forever. They never repeat. So we did not see these numbers in our list of possible rational zeros because these are not rational numbers. So here are your 4 zeros. The last part of this problem says it wants us to write the polynomial in factored form. So this is where we can use our factor theorem, which tells us that if you know your 0, then you can create your factor. So just a reminder off to the side here, we know that if you have a number, we'll just call it c. If c is a 0 of your polynomial, then you know that the quantity x minus that number, so x minus c, that will be a factor of the polynomial. So using that factor theorem, we can work backwards to create 4 individual factors. So the name of this function, remember, it was called p of x, so I'm going to name it the same here. So my function p of x, my first 0 was negative 1, so my factor will be x minus negative 1, which you know will simplify to be x plus 1. My second 0 was 2/5, so that would be x minus 2/5. My third 0 was 2 plus the square root of 3, so my factor will be x minus that quantity, 2 plus the square root of 3. And you can leave it just like that, x minus the quantity, 2 plus the square root of 3. You don't need to simplify that at all. And then our last 0, kind of separate my work for you here. My last 0, which was 2 minus the square root of 3, will become a factor of x minus the quantity 2 minus the square root of 3. And again, you can leave it just like that. The only time that I really want you to multiply and distribute any of your terms out is if the terms have an imaginary piece to them. But if there's no imaginary values, then you can leave it in factored form just like this. Now, the last thing to check before we're done here is we want to make sure that the leading coefficient matches. So the leading coefficient out here right now is a 1. I don't even have it written. Let's go back and look at the original problem. What was the leading coefficient in the beginning? Notice that this polynomial had a leading coefficient of a 5. We need to make sure that the a value, remember we called that our a value, that your a value is the same, whether your function is in expanded form, like it was given to you, or whether you have the function in factored form. So we do have to remember to come out here and put a 5 in front as my leading coefficient so that I have a factored form that is truly equivalent to the original polynomial. So this is my factored form.